So you can use the Lumin lamp either as a night lamp or as a prototyping research lamp. And I have printed this 3D part. I've designed it and printed it so it fits on this night lamp here, and this groove here actually fits at the back of it like this. But you'd have to remove the feet and then put this instead, because this one actually has the feet already on them. And then you can just keep the feet for your actual night Lumin lamp. But this is more for prototyping, so you'll need to print this part here. And then for the terminal block connectors, I recommend one that is open like this and not the cheap plastic version that you can have, because those ones you can just loosen the screw and then you can quickly put your alligator clips across, and it makes your whole experimenting journey just so much easier and so much quicker and more intuitive as well. So I actually just fitted this, and I was experimenting with the Lumin lamp, and I actually made a discovery. I'm gonna now show you a clip on how this is conventionally wired on Wikipedia. And so on Wikipedia, there's an article about the Joule fifth and some images which describe the diagram of the Joule fifth. Now, if you see this diagram here, we've got a really conventional Joule fifth diagram. Now we can see that the I call it the center tap because essentially it's the middle of the two wires. Actually, it's connected to the positive here. So we've got positive, and then it goes to the coil, and then we have a diode here, and then we've got the load, which is connected from the output here to the negative. So here I've got the same connection as the original Joule fifth on Wikipedia. So it's nothing new here. We've got the opposite sides of the coil connected to the positive side of the battery, and one side of the coil goes to the collector of the transistor, and the collector of the transistor is then connected to this red wire, which is the output. So the red wire goes to the germanium diode. So I've got a germanium diode here. You can see here the germanium diode is connected here, and then the diode goes to the light bulb, and then the other side of the light bulb goes to the negative side, just as per the original Joule fifth diagram. So here there's nothing new, but what I've discovered, and it's probably nothing new, but I've not seen this information online, so this is why I'm showing you this experiment that I'm doing here. What I've discovered is that we can switch a connection around, and we get an increase in power, and we get a current reduction. So currently the current draw is 312 milliamps, voltage is 11.33 volt, and I'll show you the oscilloscope. So the probe is connected to the start of the diode, the oscilloscope probe, and the negative side of the oscilloscope probe is connected to the negative side of the battery, which is this blue alligator clip. This is the blue alligator clip. I have disconnected the actual negative side of the PCB because for ease of the demonstration here of the experiment. So this is the actual clip lid. You can see if I disconnect this, there's the light is disconnected. There's less current draw. So look, yeah. So when the light bulb is connected, the current draw increase. And so I'll just reconnect this here. So current draw is 316 milliamp at 11.33 volt. And the discovery is that if I change the connection of the output from the negative to the positive, we actually get an increase in voltage and a reduction in current. What this means is that we are capturing the back EMF of the collapsing field, which is called a radiant spike. We're capturing this and putting it back into the system. So essentially what we're getting is that the lamp is will be a radiant lamp, a radiant energy lamp. So I'll show you here I'm going to try to zoom out a bit just so you can see. So I'm grabbing this blue wire, which is the output of the light bulb. So I'm disconnecting this. So current draw is 317 milliamp at 11.33 volt. I forgot to show you the oscilloscope shot here. So this is the original Joule fifth. Just trying to rotate the camera a bit better. And so if I just auto set this signal here, you can see that the frequency is 39 kilohertz and the volt peak to peak is 43.93 volt, voltage maximum of 43.78 volt and voltage mean of minus 1.15 volt. So this is the way that we've been showed on how to connect the original Joule fifth. This is what the signal looks like, which is a positive mostly signal. So this is the original Joule fifth connection. I'm gonna now disconnect the negative clip lid here, and I'll show you the reading so you can get an idea here. So the current draw is 321 milliamp, voltage is 11.29 volt. I'm just going to disconnect now the clip lid of the negative, so the light bulb is off. We can see that if I connect the negative, the current draw is around 320 milliamp. And this time I'm going to connect this output of this light bulb, which is was connected to the negative. Now I'm going to connect the output to the positive. So I'll show you what it looks like. Okay, now the current draw has gone down. Intensity of the light is the same. The voltage is more or less about the same. And I'm going to show you the scope shots here. So I'm just going to reset the scope shot. I'm going to show you the readings. So we've got now, you can see the voltage has increased. I'm going to zoom in a bit. So the voltage has now increased to 53 volt. We can see we've got a more, we've got a negative value here. We've got minus 13 volt, which we didn't have before. And we've got a max peak of 39.94 volt. This is the signal. I'm just going to show you the signal again. I'm going to center the signal. So this is the signal center. And also we've got less current draw going into the system, and we've got a higher voltage. So we are now feeding back the collapsing magnetic field of the coil back into the Lumin lamp. So we've got a radiant energy lamp